For today, we're very pleased to have Dag Jostein.
Very good.
I've been practicing.
Yeah.
To speak, and he's going to be talking about measuring dependence with local Gaussian correlation.
Thank you. Well, thank you very much for inviting me. It's very nice to be here. It's almost like a mini sabbatical leave, I think. So I have to apologize because this is not really in the mainstream of the seminar, the change points and the local stationarity. But I hope to come to that a little bit at the end. So here is an outline. So I'll start by giving some background about measuring dependence in bivariate data. And its theory and applications, and then I'm going to give some theory at item 2, local dependence and local Gaussian approximation, explain this idea. And then there are 4 applications. We've been looking at tests of independence. We've been looking at recognizing copulas. And then the last 2 topics, financial contagion, and that's where change points may come in. But I've not used change point methods. And then finally, financial asymmetries. And this is where local stationarity possibly can be used. So here are some literature. So the first one is covering theory. It's published last year in Journal of Econometrics. And then I mentioned these 4 applications. They are going to appear in 4 different papers. So this testing of independence is going to appear in Statistics and Computing. The copula paper has been submitted. I got the report 2 days ago. I think it's going to make it. So, and then this thing about financial contagion is going to appear in Journal of Empirical Finance. And then finally, measuring asymmetries in financial returns is going to appear in an Oxford volume. And in case you want to try this out with a package that's going to appear, our package, it's going to appear in Journal of Statistical Software. So all of this is based on localization, so to speak, of the ordinary Pearson correlation, which has been defined here for reference. And the point that we are making is that this is something that's really used for Gaussian variables, and in that case it gives complete characterization of the dependence. If you look in the Wikipedia under correlation, then there are lots of examples where it doesn't work. So, and we know, of course, that it doesn't work in many cases. But these are some cases that are highlighted in Wikipedia about correlation and dependence. And for all of these 6 cases, the Pearson correlation is 0. But you can clearly see that you have strong, quite strong dependence here in these plots. So here you have sort of positive dependence, intuitively negative dependence, and similarly for these other plots. One may think that one can resolve this, and very often it is resolved by doing a non-parametric regression. So that would reveal that you have sort of positive dependence here. But a non-parametric regression would be more difficult, of course, for these cases and for this case. By the way, please feel free to interrupt me at any point, because I'm going to cover lots of material, and you may want to interrupt me at one point or another. So I'm coming back to these examples later on in the talk, when we are going to use our version of local Gaussian correlation. So, but first let me discuss a little bit this thing that I mentioned about the possibility of doing regression, non-parametric regression. Because there was a quite early paper about this by Bjerve and Doxum in the Annals of Statistics. And the idea was just to start with the linear regression. And then, of course, you have the correlation given by this expression. And what they did was to generalize this to a non-parametric regression context. So they estimated the conditional mean, and then they defined a local correlation by analogy. So they defined it as the derivative of the conditional mean estimate. And that will be reduced, of course, to this relationship in the elementary regression case. But there is something wrong, in our opinion, about this, because this is regression, and we are looking for correlation. And correlation in regression, the y variable plays a different role from the x variable. But in correlation, you should really put x and y on the same basis. So correlation is multivariate analysis, whereas this is regression analysis.
Is there a lack of symmetry in this?
Yeah, exactly. Exactly. That's what you have. You have a lack of symmetry here. So you are sort of predicting my next slide here. So it's coming here. Yeah, it's not symmetric. So, and also it depending just on one variable, the localization, and you would like it to depend on both variables, x and y. But it has this feature that it's between -1 and +1, and the dependence implies that rho of x is equal to 0. Well, maybe I could skip this slide, but I'll mention it nevertheless, because there are many ways, other ways of testing for dependence, or measuring dependence. But this is global dependence, this slide, whereas we have been looking at local dependence. So that means defining dependence in a neighborhood. But this is global dependence right here. And I'm mentioning this because, well, first of all, it's a natural test variable. You have independence if the joint cumulative distribution function is equal to the product. So you could estimate each of these and then measure the difference. And there are many ways of measuring. This is only just one way of measuring the distance. There are many other ways. And I'm mentioning this mainly because with this Brownian distance correlation that some of you may know, that seems to be working very well. And it was a discussion paper in Annals of Applied Statistics, and it's hard to beat when we try to do it in using our local dependence measure. There's one thing that I should mention. These measures, they can only measure deviation from independence. They cannot distinguish between if there is something like positive dependence and negative dependence. You cannot distinguish using this measure because you just take squares here. Okay, so I mentioned that our measure is a measure of local dependence. So we would like to sort of be able to compute a local correlation in neighborhoods or regions of this plot. So this is a plot of returns from the FTSE and the Standard & Poor, and it's just going from 1990 to 1999. Later on, I'll present data going to 2011. The global correlation here is 0.36. And you can compute, you cannot see this, but you can compute the local correlation. I will explain later how we do this. And the point here is it's about 0.30 in the middle, and then it's increasing to 0.6 here and 0.6 here. And this is according to the intuition of economists, because they think when the market is going down here, we have large negative returns, then everything is following this trend, downward trend, and you should have stronger dependence between these two financial objects. And this is the FTSE versus German. So, and people have been aware of this for a long time, of course, and various things have been done to try to measure this locally. And this is perhaps the most popular measure used by finance people. So what they do is just to compute the correlation in a certain region, and then using the ordinary empirical correlation. So it means that you just take the region A here, and then you compute the empirical correlation just using these values that you have observed in this region. And there's a similar thing, there is soon coming a new book by Harry Joe in cupola analysis. And he is using this conditioned correlation as a means of recognizing cupolas. But he is not calling it the conditional correlation. Maybe he is not aware of this work. He is calling it pseudo correlation. What's wrong with it? Well, from our point of view, what's wrong with it is that if you have a Gaussian distribution, then this conditional or pseudo correlation will vary, will not be constant. Because you use an indicator function to cut off the Gaussian distribution, and then you do not recover the ordinary correlation. And we've tried to do differently, where you end up with the Gaussian correlation if you have a Gaussian distribution. This does not. So, for example, this so-called bias for the Gaussian. So, in case you have Gaussian data, or Gaussian distribution, I should say, and then you look at this region exceeding the 75% quantile, then you get rho equal to 0.21, and it's going to 0 for increasing quantiles, which may have something to do with the fact that tail dependence in the Gaussian, bivariate Gaussian is 0. So it's misleading for local portfolio analysis, and people have tried to correct for this bias. There are alternatives. I'm going too slowly, so I'll just skip this measure by Holland and Wang. That's one way of avoiding this problem, and we've taken some ideas from Oakland. I've given that already. Here is the idea. So, given a density function f, then we approximate f locally by a bivariate distribution. So that means that the points x1, x2, or in this neighborhood, I should say, we fit the bivariate Gaussian density. So it's given by this, and then the variances and the rho will depend on this point that you're using. If you move to another point, you'll get another Gaussian approximation. And the local correlation is then defined as being this creature here. But of course, you have to be careful when you do this, because you should keep in mind that you cannot just take any Gaussian passing through this point. It has to be tangential so to speak. So you have to fit it in a neighborhood, because otherwise you can do this in infinitely many ways, and it's not unique. So we are using this tangential, or we do it in a neighborhood and then minimize in that neighborhood. So what we've used is to, so this is to define the theoretical or population value of the local Gaussian correlation, or the other parameters as well, by minimizing this distance between the Gaussian, the approximating Gaussian, and the true density function. And we do this in a neighborhood, and we use this kernel function, and then let h tend to infinity. So this is, one can show, it has been discussed in a paper by Jones and Hjort, where they use this for quite another purpose. So I'll come back to that a little bit later. So it's related to minimizing the Kullback-Leibler distance, really, and it leads to this equation. And this has been implemented on the computer, and it's available now on Journal of Software, so you can create these local things yourself if you like. And then this has the advantage, if it's Gaussian, then the local quantities, they are equal to the global ones. So then you get the global parameters of the Gaussians, and you can have a step function of Gaussians and compute this. And we will see later, then we can look at copulas and compute it analytically, what this local correlation should be. So some properties here. So I already mentioned, if f is Gaussian, then the local correlation is equal to the rho for the Gaussian, which is an advantage compared to this conditional correlation or pseudo correlation. And also this, it's more general really. If f is a Gaussian cupola with arbitrary marginals, then this is equal to the correlation of the Gaussian cupola. So we didn't understand that in the beginning, but I think we understand it now, so I'll come back to it later, because, yeah, I'll come back to it. Range is right. Of course, in the linear case, if you have linear dependence without any noise, then you get that rho, global rho is equal to 1. Here, if you have a deterministic relationship like this, then it's 1 if the slope is positive, it's -1 if it's negative. And independence implies that rho is equal to, identically equal to 0. Unfortunately, it does not go both ways, so you also have to include these requirements about the local means and the local variances for this, to have independence. But again, it's possible to scale using analogs of coupler methods, so that in fact you have an equivalence here. So I'll come back to that. Transformations, I'll skip that, and symmetry. So this is just a simulated example. It's a student T4 with correlation equal to 0. But even though the correlation is equal to 0, you have a dependence, and you get positive local correlation here, and positive here, and negative here. Gauss, you get positive. I cannot remember exactly how the Gauss model was. Was it a one lag Gauss model? Positive here, and negative here and here. You can read more about this if you're interested in this in our papers. So a little bit about the estimation theory. So we are doing estimation then by local likelihood. And there, this reference that I mentioned by Hjort and Jones, and also by Loader in the same issue, I think, at least in the same year of Analysis of Statistics. And the recent paper by Gourier, Giroux, and Jasiak in 2012. but again, the viewpoint has been different in those papers because they are looking at the problem of estimating a density function by a known parametric family, which is Gaussian in our case. And then you estimate this local parameter, put it into the members of the parametric family, and then you get an alternative to the kernel estimate. So what has been useful for us is to look at the theory, likelihood theory that they developed. So I'll quickly go through it. So this is the local likelihood, so log likelihood, I should say. So this is our approximating Gaussian, and we look at it in a neighborhood. And then you need this adjustment factor, and you can see why. Because now we want to find the estimates by maximum likelihood and this local likelihood. Take the derivative, put it equal to 0, and then derivative logarithm is 1 over, and then you use the chain rule, so you get this. And here you get this expression, just differentiating with respect to phi. And then the law of large numbers, or the ergodic theorem, means that this is converging towards the mean, and f of v is the true density, so that's why you get this here. And then you can see you get this difference between f and phi. And when you let h tend to 0, the bandwidth, then this additional term forces the approximately Gaussian to be close to f of x. And then you can derive an asymptotic theory, and Hjort and Jones did that, although their point of view was very different. And we've extended that, it's a minor extension really, to the stationary case, or ergodic case, I should say. There is trouble here when h is going to 0, the bandwidth, because this is the score function, and it's 5-dimensional in this case, because you have 5 parameters, the 2 local means and the 2 local variance and the local correlation. And when h is going to 0, this matrix here has rank 1. So it doesn't work so well when you're going to take inverses here. So you have to do a higher order Taylor expansion to be able to get something sensible. And that sort of means that you get some strange rate conditions here. So you have to have a large bandwidth, really, at least if you do it in this way. So again, I'll come back to an alternative way later on. So these are the regularity conditions, and this theory is stated in this Journal of Econometrics paper. Choice of bandwidth is important, of course, and we struggled a lot with that. But finally, we ended up with a sort of general bandwidth choice, which is taken from the very well-known paper by Mevin Stone, cross-validation. I think it has about 5,000 citations or something like that. So we use that cross-validated log likelihood approach, so to speak. This is a weight function. So applications, I'm coming to that now. Well, first of all, we have this description of local dependence. I've shown you I've showed a few plots already. Test of independence. I'm going to say something about tail dependence and these local measures. Identification of copula models. You could use it for test of normality. We haven't done that, but there are so many tests of normality around that the competition may be very stiff. But the advantage of our way of doing it is that we can extend this to arbitrary many dimensions and then test for normality in high dimensions. So maybe we'll try that out. Principal component is, of course, defined in terms of the covariance matrix. And now we have a local covariance matrix, and you can define local principal components, principal curves, and things like that. And then what I mentioned, test of contagion and asymmetry and local correlation. So first, the Wikipedia examples. So we are going to treat those using local correlation. And what we should expect, or hopefully are getting, is that it should be positive dependence. I'm sorry, positive dependence here, negative dependence here. Well, here it's hard to say, isn't it? And here you should have a negative dependence here and positive dependence here, and similarly for this. And it works out extremely well, almost too well. So I don't know. So you see that here, this, what do you call this color? I'm not sure. Well, anyway, this color is for positive. So as I said, now we have the opportunity to distinguish between positive local dependence, that's when the local correlation is positive, and negative dependence is when it's negative. And it's supposedly, it's with the model or the goodness of the approximation, it gives quite a complete description of the dependence properties of a density. Because in a neighborhood, you approximate it with a Gaussian, and a Gaussian gives the complete description of the dependence. But it worked out very well, actually. Then I'll say something a little bit about this independence testing. So an obvious idea then, of course, is to compute this local correlation and then aggregate it. And you don't have to aggregate it over all of the space. You can aggregate it over the tails, if you like, something like that. And you can test for, the way it's done here, you're not testing for positive or negative dependence because we are squaring it. But you can test for positive or negative dependence. So at the beginning, I liked this example very much, but I'm not so enthusiastic about it anymore. So this is some aircraft data, Savotti aircraft data. And it's giving you the log span on the wings of the aircraft along the horizontal axis and the log span of the maximum speed on the vertical axis. And you can see there is sort of a very confusing scatter diagram. But this is because in retrospect, there was so many different populations involved here in aircraft. You could have transport planes, and you could have, passenger planes or whatever. So it's not so surprising, perhaps, that you get. But anyway, the point of this data set is that the Pearson correlation is 0, so to speak. If you use this aggregated measure, you get 0.4 with the local correlation. And you can compute, for what it's worth, I don't know. So this is saying that the negative correlation, that the local correlation is negative here, it's positive here, positive here. And you can get some significance levels on that by using the procedure of Jones. But I mean, these are different populations, I think, so it's, I don't know. We've also compared to this recent measure that I mentioned by this correlation distance measure, but I think I'll just skip that comparison. You can read about it in this Journal of Statistical Computing if you like, and where we also are testing for sort of tail dependence, but I have to move on, I think. Let me say a little bit about the tail dependence, though. So this is the tail index measure, well-known measure for tail dependence. Here it's formulated for the lower tail. And it's well known that one of the problems with the Gaussian distribution for in describing financial data is that it has no tail dependence. And you can express the tail dependence here. And when u is going to minus infinity, that's the left-hand side tail of this bivariate distribution, then this is going to 0, except if rho is equal to 1. So we could try to do the same thing for the local Gaussian. like that, and this now we measure the local correlation along the diagonal, going to minus infinity for both the variables. And then you can see from this that if the local correlation is bounded, then that also implies that there is no tail dependence. So if you have a positive tail dependence, it suggests that if you go very far out, then you get correlation of 1. So that means that the market is collapsing completely. Everything is correlated with correlation 1. And this can be computed, and we proved explicitly that this is the case for some of the Coppola models. If you are familiar with Coppolas, you may know that the Rosenblatt transformation is used quite a lot in generating Coppolas. So this was a paper way back in 1952, Annals of Mathematical Statistics, 4 pages, something like that. So it was not cited very much in the first 15 years perhaps, or something like that. But then the Coppola came along, and its citation rate shot up. And so it's what is proving it that is really that if you have a density function, then you can represent that as a function, a bivariate function of 2 uniform random variables. And we've our own version of this because we want to replace uniform random variables by standard normal random variables. And we were very hopeful that we could use this for computing the explicit local correlation for virtually all Coppolas, but it didn't work out so well because this, as is stated in the paper by Murray Rosenblatt, this is not unique. So it depends on the way that the sequence of whether you start with the x1 or x2 matters for this function g. You get a different function. And that we need the uniqueness. So, and we get uniqueness for exchangeable Coppolas along the diagonal. And of course, there is this story that some of you know that when Murray Rosenblatt was interviewed by Richard Davis and David Brindier, this is called the Rosenblatt transformation. And he didn't know about the Rosenblatt transformation, haven't heard about it. So when he was asked whether he knew about the Rosenblatt transformation. So it didn't work so well, but along the diagonal, you have uniqueness, and then you can compute an analytic expression. Looks quite messy, so it's not easy to tell what this is saying about the Coppola along the diagonal, but you can compute it at least, and it's not a numerical derivation. You can compute this formula, and the Gaussian Coppola yields again the right thing. It's giving you a row. This is if you're familiar with Clayton with Coppolas. So Clayton Coppola is one of the major Coppolas used by finance people because it has a stronger dependence when the market is going down, so to speak. So we've used our analytic formula to compute the local correlation along this diagonal where x is equal to y. So instead of this plot, we just get a plot of the local correlation along this diagonal. And here you can see that, so these are for various values of the Kendall's tau. If you have a strong dependence, then it goes up quite fast, relatively fast, and then it approaches 1. So that's the property that I talked about. So you can actually prove that for the Clayton Coppola. And Gumbel and Frank Coppola, we have similar things. There is a goodness of fit test. Well, there are various ways of figuring out which Coppola you should use for a given data set. And one of the most popular ways of doing it is using the Akaike criterion. But that is just giving you the best approximation in terms of this criterion. You would like to know whether the best chosen coupler really fits well. So you need a goodness of fit test. And there are many such tests around. This is a reference that we've used to compare, which seems to be sort of at least approximately an industry standard. And where they have compared, where they've used this goodness of fit test, it's a non-parametric goodness of fit test, comparing empirical and parametric couplers. So a natural approach then from our point of view is to compute this local correlation, this is like we did analytically, and then we can compare the estimated one. But here we're coming to, at first we didn't do so well, and here is just something that is, I think, is essential in this connection. So we've introduced what we called a canonical local Gaussian correlation. Because if we want to compare with the cupola has this two-stage thing where you first find the marginals and then you model the dependence just in terms of the cupola. And it's invariant to transformations of the marginal distributions. Whereas our local correlation depends on the marginals. And then the question is, should it depend on the marginals or not? And I can remember one meeting we had a big discussion about this. And at that meeting, I ended up saying that I thought it should depend. Well, it does depend on the marginals, of course. But should it? Should you find a version where it does not depend on the marginals? At least that's what is convenient for this goodness of fit test for cupolas. So what we've done is to, instead of transforming to the uniform marginals, we transform to standard normal marginals, which is very easy to do in practice. It's just, taking the normal scores from the uniforms. And we think this is more natural because lots of data is not on the uniform scale, but it's on, a t distribution or whatever, something not that far from the normal distribution. So we've used this is what we call canonical local. So this does not depend on the marginals then. And this also explains this thing that for the Gaussian cupola, rho is a constant. It does not depend on the marginals. So this is coming from this. And you can even, if you like, formulate the Sklar's theorem here, where you transform your marginals to standard normals instead of transforming them to uniforms. And the advantage is, unfortunately, I do not have a plot now, but I could compare a plot. If you've seen these plots, when you go over to the uniform scale, it's very difficult to see tail dependence because, you get lots of points crowded in one corner, very hard to decide, really, on that scale. And that's also why Harry Joe and others also, I'm sure, in his book are using these plots where they do not use the local Gaussian correlation, but they use this conditional correlation, or pseudo correlation, to sort of try to see what's going on. So I've explained that already, I think, because there is really a very substantial improvement on their results. And intuitively, I think it has to do with the fact that if you use the uniform, you really compress things in the tails. So you cannot see that clearly. So this is just a transformation of dot back. And goodness of fit test, we are just then using the difference between the empirical local correlation and the one that we can compute, and then take squares. We use this the bootstrap to get the level right in the null situation. And then the bandwidth, we used a different bandwidth algorithm, but that's not so important here. Oh, I see, this does not come out so well. So, Okay, I think you'll just have to take my word for it that you get very, very substantial improvements. So, for example, here from the Frank cupola, you get a power of 9.2 for this test that I mentioned, and it's going up to 80, 0.80. So it's enormous improvement. Not that much improvement in all of the cases, of course, but it's pretty uniform improvement. But you can see the details in this paper. Hopefully it's going to be, it looked promising that it's going to be accepted. And you can, of course, you can get a preprint from me. And then there is a famous data set among insurance people and a couple of people also. Danish fire insurance claims. It looks like this, and you do not really have to know what it's all about. It's just this data set that you see here, and the problem is to find a good cupola for describing this data set. Looks like a Gumbel cupola could do the job if you look at it superficially, because the Gumbel cupola has the property that's larger dependence in this end instead of in that end, which is the case for the Clayton cupola. So the AIC criterion, if you use that, ends up by recommending the, not surprisingly, the Gumbel cupola. Nevertheless, if you use this, check this locally, local correlation, this is the, let's see, this is the empirical local correlation along the diagonal again. And this is the parametric for the Gumbel cupola. And you can see that the Gumbel cupola assigns too much dependence in this tail of the data. So it doesn't fit so well, actually. And these are confidence limits computed by Bootstrap. So what we found was that a reversed cupola, Clayton cupola, that passed the test. So you just put it on the head, so to speak, a Clayton cupola, and that passed the test. Did very well. Okay, finally, change points. And perhaps local stationarity. So we have this paper that are going to appear in Journal of Empirical Finance. So let me first explain a little bit about contagion. So the idea is that financial markets, they become more interdependent during a financial crisis. And there are several studies then about this. And there are also many definitions of contagion, what it means, can be defined in many ways. So we've sort of used, there's a famous paper by Forbes and Vigabon in Journal of Finance in 2002, where they concluded, they used this conditional correlation and adjusted for bias, and they concluded that, well, there isn't really that much contagion. It does not increase that much. It's just a lack of adjustment for the bias that has brought about these apparent results. And after that, there has been several papers claiming different conclusions. So we've tried to use this local Gaussian correlation to examine this. And I've already mentioned the existing methods. Yes, and there are several other things also. You could use cupolas, and you could use regime models, not surprisingly, Markov switching models. And we studied occurrence of contagion for 3 different crises: Mexican peso crisis, East Asian crisis, and the financial crisis. And for each of these, we had what we call the stable period before the crisis, and a turmoil period after the crisis. But the point here is that the change point has been determined by economists. When did the financial crisis start? I think the economists, they have an opinion about that. It started on a certain date. I think it was August, let's see, commented here. Well, then we use a bootstrap test for finding confidence intervals and the testing whether if you had a change. So I don't have time to go into details on that. So I'll just look at the finance crisis because I want to get to this asymmetry as well. Yeah, here is the timing. The finance crisis started August 8th, I think, 2007. So something happened then that most economists agree on was a crucial date. Maybe the collapse of the Lehman Brothers or something like that. But of course, what one could do here is to try to use change point methods and to see if the change point in fact is earlier than that. We haven't tried to do that. Also, I sort of suspect that, is it reasonable to expect that you get a sudden change? I'm not so sure. There's maybe more of a gradual change. But one could at least try to look at it. Yeah, let's see. That's the data that we looked at. We looked at the US, so that's another thing. In these papers, there is a country of origin, so you decide that in advance. So, but you could have a causal analysis, of course, like grain causality or something like that. You could try to do that locally or globally. But then the US is the origin of this financial crisis. And there are many countries involved. We looked at the US versus United Kingdom, Germany, France, and Norway. And here are the exchange rates. So here, what this is a plot of the local correlation along the diagonal where x is equal to y. This is the value of the local correlation. So you see 0.5, 0.6. This is in the period before the crisis. You get a plot like that. You can get confidence intervals. And after the crisis, 2-year period, you should expect higher correlation, and especially in the tail, perhaps, in the lower tail. But you see that, well, you do get the largest difference, well, maybe in the middle also. So this is a nonlinear analysis, of course, and it gives you more detail than just saying that the correlation is going up. So here you get a more detailed picture. And then we've done something similar for the other countries. So here is parallel, more or less, the US and Germany. US and Norway, it's not parallel. The US against United Kingdom, the smallest difference before and after. I don't know why. And you can test this using bootstrap test, and at the 5% level, this was not even statistically significant, but close to, the p-value is close to 0.05. For the others, it was significant. We've also, at the suggestion of the referee, looked at the current data, so quite a long time after the crisis, and it turns out that these high local correlations, they persist. They are still there. And then this asymmetry of symmetry and asymmetry of financial markets. Local stationarity, possibly, because this is the FTSE against the French index, and here is from 1987 to 2011. And again, this is the standardized returns when x is equal to y, so it's along the diagonal. So this is the returns here. Here you have a negative return, so the market is going down, and since it's along the diagonal, it's enough with just one axis here. This is the value of the local correlation. And you can see that, as expected, you get higher local correlation when you are approaching when the market is going down, but not that much really. And you have this thing going on here when the market is going up. But then, of course, this is non-stationary, because you cannot expect these relationships to be the same over 25 years. The lack of doing a local stationarity analysis, they just subdivided the interval into 5-year intervals and looked to see if there were significant changes. Yeah, this is the same time period. This is the first time period going from 87 to 91. And you can see that there was a crisis in 1987. I've forgotten what that crisis was called, but it was really very large crisis at that. And this is reflected. It's dominating this whole period, really, here. So you have strong correlations here, and not much of an upturn, really. But you'll see, and there are confidence intervals here. But you'll see that this is very different then again from the next period. So this is clearly non-stationary.
Why is the x-axis, previous it was -2 to 2, now it's -4 to 4, and now it's -3 to 3.
Let's see.
But
It's -3 to 3. It's -3 to 3.
Before it was -4 to 4. Maybe I'm blind to that.
Well, I'm closer. It looks like it's -3 to 3. Or maybe, let's see. I'm sorry. I could be. Yeah, here. Yeah, here's -4. That's because apparently there were some larger. When you look at the.
So the data set's much longer, so you have much more data in the tails in this case.
Yes, that's right. But the next one also has many data, so I'm not sure. I have to look at that. It's the first time I haven't noticed before you said that. Nothing wrong with your eyesight. Okay, so let's see. Yeah, where were I? So this is this disaster. So there was a economic disaster on the stock markets in 1987, and now you can see it's different. 92 to 96, almost. If you have a straight line here, then that indicates that you have a Gaussian relationship, because then it's constant. 1997 to 2001. This is interesting. 2002, 2006. Here you can see that you have, market is going up, and that's during the Clinton era, because the economy is stupid. The economy went very well in that period, and this is reflected in this plot. I'm sorry. Yes, this is reflected in this plot, this region. And this is the financial crisis. So we were disappointed that we didn't get more here in this end. So I don't know, but it's a fairly high overall local correlation here. And I've tried to understand this is going up, and then there is a high correlation when it's going up. And economists have told me that there's something called a suckers rally. So when the market has been going down, then there is a period when it's going up for a couple of days, and then there is a strong correlation with this going up, and that's called the suckers rally, I've understood. Monthly data, you get very different picture. And that's also reasonable, I've been told by economists. Okay, so yeah, I'm more or less on time, I guess. So it gives you a much more detailed picture of an ordinary correlation population that can be defined and can be estimated by local likelihood, and I've given you these 5 applications. Thank you very much.
So does this in some way relate to principal curves? So if you had your examples and your data kind of lied on some low-dimensional manifold, you want to
I see your point. I don't think so, because principal curves has to do with, as far as I know, nonlinear principal component analysis. So there are principal curves if you do a local principal component analysis. Then you get these local curves, local principal curves. But these are just the curves that I'm displaying. It's just a way of simplifying the presentation, because really I should present a two-dimensional plot each time, because you have x and y variables are going, say, from -4 to +4, each of them. And then you should have a plot like I had in the very beginning. Wrong way. Yeah, like this. So in fact, I should present plots like this all the time, but it's not very satisfying from a visual point of view. So these curves that I've shown you is just an extract of this plot along the diagonal.
Yes, I guess I was wondering whether, if you've got that local correlation,
yes,
whether you could use that to actually define a principal curve. So
you can, I think, but I don't see the connection here. But if you go to local principal components, so if you look at the
oh yeah, no, I didn't mean
yeah,
the later
okay.
bit. I was just wondering whether you could use it to define this, the idea of local correlation you could use to create equivalents to principal curves.
Yes, you can, but that principal curve has to do with principal components, and there is nothing about principal components here. This is just a bivariate analysis, but you can extend it to a d-dimensional analysis, actually. And then you can define, then you have this correlation matrix, covariance matrix, and then you have local entries in that matrix, and you can use that for looking at principal curves. So we've just started doing that, so it's a very natural thing to do. And so, for example, trying to extract a circle from a very confusing scatter plot seems to be possible to do using this approach.
You mentioned that you can recover the global correlation for normal distribution.
Yes.
This is a theoretical property, or you can do it in practice?
No, this is a theoretical property. Yeah. So from the way it is defined.
Okay.
So intuitively, it's quite clear, because if you just look at the not the bivariate case, but the scalar case, and you could do a local Gaussian approximation, and if you do that in the neighborhood, then you end up with exactly this curve.
So
for the Gaussian approximation.
Play a role there.
Yes, it does. Yes.
Yeah. Okay.
So the estimate, of course, is varying. Yeah. But when it's going to 0, it will give you this curve. So that's one advantage, we think, of this the R scheme, as compared to this conditional correlation or pseudo-correlation.
You also mentioned that you use the cross-validation to choose the H.
Yes.
You cross-validate the density estimation, or what?
Cross-validate the?
When you do the cross-validation, the criteria was defined as estimation for density function.
Yeah, it's the likelihood. Likelihood cross-validation. Yes. So.
You see, the plot you present are very illustrative. I just wonder how crucial the H is. For example, for the data you used from this.
Whether it's robust, you mean?
No, for example, the data you used for this downloaded from the Wikipedia, a few plots. Wikipedia, the data you used.
Yes. Yes, I think I'm not sure that he used actually the cross-validated bandwidth for that situation, but it's fairly robust, I think.
I just wonder if I choose a non-boundaries
yes.
in a local area,
yes.
just a circle. then it may end with a correlation, local correlation theory.
Oh
Bring
yeah,
out the
yeah,
different
yeah, it
correlation.
can. But well, first of all, you have to use a fairly large bandwidth because of this. I was lucky enough because you have this second-order Taylor expansion, and you have to use a fairly large bandwidth, larger than in traditional non-parametric estimation. So that means that the plots are much smoother. So if you see lots of deviating observations in a plot, that hopefully should be picked up by the cross-validation criterion. And if not, just by looking at it, this is too small bandwidth. But I'll ask Geir Berntsen again how the bandwidth that he used for the Wikipedia examples. It looks sufficiently good. But the bandwidth formula, no, I cannot find it right now. But it's a local likelihood bandwidth cross-validation, and we used the approach by Mervyn Stone, his paper. And we struggled quite a lot with that, the bandwidth problem, before we used this. This formula seems to work quite well. This was an issue, of course, in the reports from the referees.
Not me.
No.
Other questions? No? No? Then let's thank back again.
Okay.